Good day, everyone. My name is Srinivasan, and I'm here with my co-authors Giridhar, Shyam, and Aruun Kumar from AWS. Today, we're presenting Sentinel, an autonomous agent-based observability framework for cloud-native systems. Let me start with a challenge that every SRE team knows really well. Modern cloud-native systems, microservices, containers, and multi-cloud deployments demand robust observability. Yet, establishing that monitoring baseline remains a manual, time intensive, and largely reactive process. SRE teams spend days, sometimes even weeks, discovering infrastructure, reasoning about what metrics matter, setting thresholds, configuring dashboards, and wiring up alerts. And every time the architecture evolves, the cycle repeats. Our approach is Sentinel, which flips this model. It's an autonomous LLM backed agent framework that bootstraps observability for your cloud infrastructure. You give it minimal seed context and it self discovers your topology, reasons over monitoring, strategies, configures alerts, dashboards, and critically escalates to human operators when it reaches its confidence boundaries. Our key contributors are the Sentinel agent architecture built on MCP servers, the Stop Bootstrap protocol, a human in the loop escalation model, and experimental validation showing significant reduction in time to observability and SRE workload. So let's start with the Stop protocol. There's an inherent bootstrapping problem in situations like these. How do you give the agent enough context to start without burdening operators with extensive configuration? That's exactly what the agent is supposed to replace. Our answer is STOP, System Topology and Observability Profile. It's a lightweight JSON schema built on four principles. Minimality, so you include only what the agent cannot discover on its own. Extensibility, optional fields and custom tags for domain specific context, which you can continue to extend. Portability, so that it's cloud agnostic with provider specific type blocks. And human readability, so that an SRE can author it in minutes. A stop document tells the agent, here's the environment type, here are your access boundaries, here are some core topology signals, and hints about criticality and compliance. The agent does the actual discovery, while stop just tells it where to look and what to expect. Now that we've seen that, let me walk you through the Sentinel's architecture. The system comprises of five components operating in a coordinated pipeline. The first is the LLM reasoning core, which is the brain. In our experiments, we used CloudSonnet. It maintains working memory of the environment, orchestrates the workflow, and applies domain expertise in observability best practices. As the environment model grows, it uses structured summarization to manage context length. The MCP2 layer comes next, and this exposes the agent's capabilities through four functional groups. The discovery tools, which are read-only infrastructure enumeration, for example, EC2, RDS, ECS, etc. Telemetry query tools, like metrics and logs inspection to assess existing signals. Monitoring configuration tools, so that it can create alarms and dashboards. And notification and escalation tools, so that the human operators can be alerted. Importantly, the agent operates under least privilege. Three permission tiers: scope to read, query, and monitoring write only. No IAM or infrastructure modification is ever permitted. The discovery and reasoning engine comes next. This drives the iterative discovery loop. The monitoring configuration engine, which translates reasoning into concrete alarms, dashboards, and metric filters. The human in the loop escalation manager will handle confidence based escalation. And these are essentially the components that bring Sentinel together. With that, my colleague Giri will walk us through the next sections of the presentation.
Now that we've seen the architecture and the stop protocol, let me walk you through how Sentinel actually operates, its four-phase lifecycle, and how we validated it experimentally. Phase 1 is the bootstrap and discovery. Once the agent receives the stop document, it uses the entry points as seeds and enters an iterative discovery loop. It starts broad, listing all resources across scope regions and VPCs, then progressively drills into each resource to understand configurations, dependencies, and existing telemetry. The stop hints around the criticality and compliance direct the agent's attention, so high priority areas get examined first. Phase 2 is the observability reasoning. Once the agent has built its internal model of the environment, it moves to reasoning. For each component it discovered, it asks, what are the critical signals? What thresholds make sense? What log patterns indicate something is wrong? And how does the component's health affect the overall system? The output of this phase is what we call a monitoring intent specification. Essentially, it's a structured plan that describes what should be monitored and why. Importantly, this plan can be inspected or reviewed by a human before any configuration is applied. We deliberately separate the reasoning from action, giving operators a checkpoint before changes are made. In phase 3, monitoring configuration phase, the agent translates the intent into concrete artifacts like alarms, composite alarms, dashboards, log metric filters, and metric math expressions. One important principle here is that agent supplements the existing monitoring but never overwrites it. Phase 4 is continuous monitoring and escalation. The agent periodically reviews alarm states, classifies incidents, and applies confidence scoring model. When the confidence drops below a configurable threshold, it triggers human escalation protocol. But before notifying anyone, it assembles the metrics, logs, and traces into a structured investigation package. This means the receiving engineer arrives with full context already prepared, significantly reducing time to diagnosis. So, how did we validate this lifecycle? Let me walk you through our experimental setup. We built Sentinel using Strands Agent SDK and deployed it into Amazon Bedrock Agent Core. For system under test, we set up an AWS environment that mirrors what you would find in a real production account. We created EC2s, ECS, and EKS for compute, RDS and DynamoDB for database, Lambdas and SQs for serverless workloads. The goal was to represent the kind of heterogeneous cloud-native system that SRE teams deal with every day. We evaluated the setup across 3 metrics: time to observability, which is the wall clock time from agent initialization to achieving a complete monitoring baseline; alert coverage rate, the percentage of components with at least one critical signal alarm; and mean time to detection, the time from incident occurrence to the agent detection and notification. Aruun will now walk you through what we observed across these metrics in our experiments.
So let's look at what Sentinel actually delivers in practice. We evaluated the framework across 3 dimensions: how fast it bootstraps observability, how comprehensive its alert coverage is, and how quickly it detects faults once monitoring is in place. Starting with time to observability, this is the time it takes to have a fully functioning monitoring baseline. For small environments, Sentinel achieves this in about 10 minutes. At medium scale, it takes roughly 14 minutes, and even at 100 plus resources, we are looking at 32 minutes. To put that in perspective, this is a task that typically takes SRE teams days of manual effort. Sentinel does it in under 35 minutes with no prior knowledge of the environment. You'll notice a roughly 2x jump beyond 50 plus resources, and this can be attributed to context summarization overhead, but this can be solved using a multi-agent decomposition. Next is alert coverage. We measure this as the percentage of discovered resources that receive at least one meaningful alarm. At small scale, the coverage was 90%, at medium scale, about 88%, and even at 100 plus resources, we maintained a 80% coverage. Importantly, this is achieved with absolutely no prior knowledge of the specific environment. The agent uses its knowledge base to infer appropriate alarms, even when live telemetry is sparse, which is a key differentiator from threshold learning approaches that need historical data to get started. The modest decline at scale reflects edge cases with novel resource configurations, and this is precisely the failure mode or human in the loop escalation path is designed to catch. Finally, MTTD, the mean time to detection. We ran 20 simulated fault injection scenarios such as CPU saturation, database connection exhaustion, application error rate spikes, etc. And across all fault types, Sentinel detected and escalated within 2 minutes of alarm triggers, demonstrating consistency and reliability. This confirms that once the monitoring baseline is established, the bootstrapping investment pays off immediately. So, what does this all mean? Sentinel demonstrates that LLM based agents can autonomously bootstrap and maintain cloud native observability, reducing days of SRE effort to minutes, maintaining over 80% alert coverage even with no prior knowledge, and detecting faults within 2 minutes of occurrence. At the heart of this is a stop protocol, a deliberately minimal schema that gives the agent just enough context to begin effectively self discovery without requiring the exhaustive manual configuration that defines traditional monitoring setup. But perhaps most importantly, Sentinel repositions SREs through intelligent escalation with pre assembled investigation context. Human expertise is engaged at the right moments for the right problems. This is a practical step towards infrastructure that understands and monitors itself, freeing reliability engineers to focus on higher order problems rather than the operational mechanism of monitoring setup. As LLMs and agentic frameworks continue to mature, we believe autonomous observability systems like Sentinel will become a standard component of cloud native operations. We offer this work as a contribution towards that future. Thank you.